I make a table right here, a summary of everything that we did, that we've done so far, and everything that I want you to know from chapter 3 here. Okay? Because it's always helpful that when you finish a chapter, try to write down, like what the chapter is about, and then try to make clear up all the differences between the cases and things like that. So now, let me run over this one real quick right here. The discrete random variable. You are given a Jones frequency function, or sometimes they call it the Jones, what is it? Probability density function, PDF. Yeah. Okay, so it's going to be something like this in two variables, x and y. And suppose that you have that Jones frequency function, and now you want to compute, like when you keep one variable constant, can you compute the density function for the other variable? You see what I mean? For example, right here you have a function of two variables, x and y. Let's say that if you keep y constant, y equal to 1 or 3 or whatever right there, and then now you can see that that Jones distribution is going to be a function of one variable only, x, because y is held constant, right? So how do you compute that? And by the way, that is called the marginal frequency function. And of course, you can also play another game. You call x constant. How do you compute the y? Right? So those two are called the marginal frequency functions. And the way to do it is this. For example, if you keep y constant, then the probability right now is just a function of x. So how do you compute that? Well, you just sum over all the x. Correct? All the x, because now you hold y constant. That's the explanation for that. Okay, and that's how I usually think of it. All right? The Jones density function, if you hold one component constant and you have only the other variable, so now you compute the probability or the density frequency function for that, where you just sum all over x, just like in the past. Because now if you hold y constant, then it's just like in the past you sum over x, right? And likewise, if you want to compute the marginal y right here, you just hold, if you want to compute the whatever, which one do I want now? Which one did I finish talking about? You know what I mean? If I hold y constant, it's going to be a function of x, and you sum over x. And now, what is the other one? So therefore, if I want to compute the marginal y, then I hold x constant, and I'm going to sum over y, for example. And now, another concept is you have a Jones, whatever you call it, CDF. Because if you have a frequency function, t right here, then you can also form the CDF, right? Because if you have discrete, then you sum everything up, you're going to have a CDF, right? And now, if you have CDF, and then now you have, let's say, n variables. How do you say that those n variables are independent of each other? Well, they're independent if and only if the Jones CDF right there factors into something in the first variable multiplied by something in the second variable, and then so on and so forth. Right? Okay, and if that is the case, then you say that they are independent. Yeah? You know that one is a very strong assumption. For example, I can give you in general just pure function, let's say function of two variables, x and y, any function of x and y. You cannot really, in general, you cannot rewrite that function as something in x times something in y. Correct? I can give you an example right now for, for example, if you have this function, f of xy right here equal to y times, like sine of x squared plus 1 right here, and then, I don't know, plus ln x right here. Good luck, Stephen, there and rewrite this function right here as something in x times something in y. You see, in general, you cannot do that. And you see that Alright, so not all the time that you have a function of two variables that you can calculate into the product of two functions. Like that. And if they do, then you say that in this case right here they are independent. Is that clear? Right? And the next concept is about what is it? Conditional distribution. Like in the past, if you have two events A and B, how do you compute the probability of A given B? In the past, how do you compute the probability of A given B? You use what? Probability of A intersect B, right? Divided by probability of B, right? Or if you cross multiply, then this is the same thing as saying the probability of B times probability of A given B right here is probability of A intersect B, right? Same thing. Now, we're going to use exactly the same definition for this. Now you have a joint distribution, right? And now you want to compute the probability of the variable x equal to something, given that y is equal to something else, right? Then how do you do? Well, naturally I'm going to define it like probability of x equal to xi intersect with y equal to yj, right? Which I'm just going to write as a comma right here, right? That's a joint distribution, so I write that, divided by the probability of the condition right there, namely y equal to yj, right? Or in math notation, you can just write it like this: P of x sub y, xi, yj over P sub y of yj. Or if you cross multiply, you get exactly this guy. Is that clear? So for example, let's look at this guy right here so that you see what I'm talking about. Let's look at a concrete example where we draw a dice or something like that. Or, you know, like toss a coin, maybe. Where's that? Okay, here's the one. Look at this one for a minute. If I toss a coin 3 times, and x right here is the number of heads on first toss, and y is the total head on 3 tosses. We already calculated everything. So what are the numbers right here? This is 1/8, right? Look at your notes, we already calculated that. So let's move quick right here. This is 0, and this is, let's say, 2/8, and this is 1/8, and this is 1/8 right here, and this is, let's say, 2/8. And y equal to 3 right here is 0, and this is 1/8, right? So with that in mind, for example, what would you do if I ask you to calculate the probability of, let's say right here is x. Okay, sorry. Sure. X equal to, I don't know, I don't care right here. Let's say x equal to 0. And given that y right here is 1. Okay? See what I'm asking you to do? Now, how do you do this one? This one right here is first, is the probability of what? X equal to 0 and y equal to 1, correct? Divided by probability of y equal to 1. Is everybody clear right there? And now you just have to look at the table and see what is the probability of x equal to 0 and y equal to 1. X equal to 0, y equal to 1. Is it 2/8 right here? Can you see that? So therefore, is it the same thing as a quarter? Right? So this one is 1/4 divided by the probability of y equal to 1. What is the probability of y equal to 1? Probability of y equal to 1 is what?
Marginal y.
That is exactly the marginal y, because this thing right here, can you see that this one is just like py right here, right? The marginal y. Okay? And the marginal y, how do I calculate the marginal y?
It's y sum of
The marginal y when y equal to 1 means what? Means what?
Fix the y. And
You
the
fix the y equal to 1 and then you sum over x, correct? So now what is that? fixed y equal to 1 sum over x, that means you sum what? Down or up or across?
Down.
Down, what column? Column y equal to 1. So can you see that one is 3, 8? Whatever that is, you just calculate it out. Is that clear? Right? And let's do another one right here. How about probability of x equal to 1 and y equal to 3? Given that y equal to 3. How do I do that? Probability of x equal to 1 and y equal to 3 divided by, this one is the marginal y right there, of what? Y equal to 3. Well, now you know what it is. Probability of x equal to 1, y equal to 3. What is that? 1/8, right? Divided by the marginal probability of y. What do I mean by that? Keep y equal to 3 right here and then you sum over x. Right? Correct? What is that? Y equal to 3 sum over x, that's 1/8. Alright? Is that clear? And now, let's do a few more. Instead of this example, we worked on this one so many times already. It's getting boring. So let's look at this guy right here. For example, suppose that some John density function right there, pxy, is given by the value of p at 0, 0 is 0.4. The value at of p at 0, 1 is 0.2. And the value at p1, 0 is 0.1. And the value of p at 1, 1 is 0.3. Okay? Now I want you to compute the probability of x given y, where x is 0 and y is 1. Alright, and the other one as well. So just look at the first one right here. Compute this guy. Alright, so now how do I compute that? I need to first compute what? Probability of x equal to 0, y equal to 1, and take that one divided by the marginal, right? Probability of what? Y equal to 1. Is that clear? So right here, I'm going to do it. First, I just have to form the quotient of those two. So let's calculate those two first. Now, probability of y of 1 right here, that's the marginal, right? So what is that? How do I do it? Well, I'm going to keep what? Y equal to 1 constant, and I'm summing over what? Summing over x. Alright? So what is that? It's going to be, okay, so now 1, so where is 1? Where is my 1? Okay, it's going to be the second and the fourth, correct? So it's going to be 0.2 plus 0.3. That's why I got 0.5 right there. Is everybody clear? And now, I'm going to use the formula that we just discovered. Probability of x given y is just probability of xy right there over the marginal probability. So probability of 0, 1, right there, they told me that's 0.2 over py at 1, which is 0.5. So I can just cancel the point and point right there. It's just 2 over 5, 2/5. Is that clear? And likewise, if I want to calculate the probability of x right here given y at the point 1, 1, so I just have to look at p of 1, 1, which is 0.3 right there, divided by py at 1 is 0.5, so it's 3/5. Is everybody clear? Alright, and now be careful, you know, like I really don't want to use the words, you know, like use some across or some down or something like that when like the book does, because, you know, like what if, for example, in the problem 1 right here, because I received a couple of emails from you guys, why is it that, you know, like in the example over here, when I try to compute the marginal density function for y equal to 1, for example, for y, how do you say it? For y equal to 1, then I'm going to sum over x, right? Correct? That means that I'm going to sum across, right? And then some people ask me, why is it that in this case right here, I I sum across and I got the wrong one, the wrong thing. Well, because they twisted the other way around. Can you see that? Over here, the problem, they list y this way and they list x this way, right? And over here, they list x this way, y this way, all right? So that's why I don't really care about.
It's symmetric, so it shouldn't matter.
Yeah, but I mean, like you see, in general, it might be a problem, right? So in general, if you want to find the marginal density for y, what does that mean? You know, like for example, over here, if I want to compute py, y equal to 1, that means I hold y equal to 1. I sum over x. Okay? That's all it is. All right. So I hope that this first part right here is clear. The discrete random variable. Okay? That one is clear. Then now the next one that we talk about as well is the continuous random variable. Now for the continuous, instead of giving you the density, whatever you call it, the John, what's the word? Frequency function. I'm going to give you the John density function, f of xy. Of course, for it to be a density function, I integrate over the region right there. It's got to give me 1, right? And if you want to compute the probability of xy right here in some set A, you just have to double integrate that one over that set A, correct? It's just like in the past, if you want to compute the probability of a function of one random variable x between A and B, what do? You integrate the function given right there from A to B, right? Over here, it's exactly the same thing right here, but I don't write it as, you know, like A to B or C to D, because in two-dimensional thing you can have some weird shapes, not just rectangular or something like that. So I just write it as A. And now, like in the past, when you have the one variable case, if you want to compute the John CDF, you just have to integrate the, whatever you call it, density function from negative infinity up to x and negative infinity up to y, for example. That's what you have right there. And then notice then that if you take 2 times derivative of the capital F right there with respect to x first and then y later, you get back exactly the density function as it should be, right? So therefore, in a way, you know one, you know the other. That's why for me, I don't really care. Give me one, I know the other. Okay? And now, again, just like the discrete case, if I hold one variable constant, then the John density function or the John CDF function right there is going to be just a function of the other one variable left, right? So therefore, you will be able to determine the, whatever you call it, marginal. Alright? The marginal density or the marginal CDF. Right? Okay? Right here, for example, if you want to compute the marginal CDF, let's say that with respect to x first, right? Remember, CDF means what? The cumulative, right? Distribution function. So in a way, if you have a discrete case, that means that you sum every possibility, all of them up from negative infinity to infinity. If you are in the continuous case, that means you integrate, right? CDF right there. So therefore, marginal CDF, what does that mean? If I just want to compute marginal CDF with respect to x, what does that mean? It means that my y right there are being held constant from negative infinity to infinity. Is that clear? And then for x, I just integrate from negative infinity up to x only. Does that make sense? Alright? And you know, like, because of I use the x up here as the limit. So therefore, just to avoid confusion, I'm going to call this one u right here. No, where is it? This one right here to be u right here instead of x. That's all. Right? And then likewise, if I want to compute the marginal CDF with respect to y, what does that mean? The x right there is some constant. I sum it already from negative infinity to infinity. Right? only y right there, I will integrate from negative infinity to y. Alright? And then because over here I already used y, so I just change this one to v. That's all. Is that clear? Right? And of course, there are two other things as well, marginal densities. Right? What do you think they are? Well, if you want to compute the marginal densities with respect to x, you just take the derivative of the marginal CDF with respect to x. Right? So therefore, if you take the derivative of this thing with respect to x, the derivative cancel with the integral, and then you have just integral from negative infinity to infinity fxy, and then this is dy. Alright? And then the marginal density with respect to y, you take the derivative of this thing right here with respect to y, so you have that. So therefore, the message to take home right here is that the marginal densities with respect to x right here, you just integrate the density function over y. And then this thing you integrate over x. Is that clear? Right? And now, if you have n variables, x1, x2, x3, and xn, how do you determine whether or not those are independent of each other? The random variables are independent of each other. Well, what do you think? If the how do you say it? The Jones CDF factors, right? What do I mean by that? The Jones CDF right there, f of x1, x2, xn right there is equal to f of x1 times x1, f of x2 times x2, so on and so forth. If that is true, then they are independent. Correct? By the way, this statement right here is the same thing as saying that the density, the Jones density function factor, they are the same. Why? Because they are related to each other. One is the integral of the other, or likewise the other one is the derivative of this one. Right? So for example, I'm going to tell you right now, I'm going to give you a quick proof right here. You know, this statement right here, for example, if you just take two variables, x and y, so that is complete, right? So x1 is x, x2 is y, and that's it, right? So by definition, f of xy right here is independent if and only if what?
Can you slide your paper up?
Oh, sorry, sure. If and only if what? F x right here times f y, right? Oh, by the way, this thing right here, sometimes people write it like that, f of xy, alright? This one is the definition. I claim that this one is the same thing if and only if little f of xy right here also factor they're equivalent. If one factor, the other factors as well. Well, to see it this way, for example, this one implies this one right here. In other words, how do we say it? The CDF factors, then the density also factors. How do I show it? Well, let's say that I go this way, so therefore the assumption is this. Correct? Now I want to show that this density function also factors. How do I show that? Well, if this thing is equal to that, then what do? Remember this thing right here, you take two derivatives, right? You're going to get this. So therefore, if I take the derivative right here with respect to x and y right here, then this thing right here is the same thing, right? Yeah. And now, what is this guy? By definition, f of xy, little f xy, correct? And now, what is this thing? Well, because this is a function of x only, this is a function of y only. So first, if I take derivative with respect to y first, for example, what do I have? I will have f of x times f prime of y. Correct? And then I take derivative of that one with respect to x, and we have f prime of x times f prime of y. Yeah? So therefore, f prime is just little f. So this one is exactly f of x times f of y. Right? And likewise, you can, if you are given this, you can also show that that one is that. You just have to integrate. That's all. Right? So I say that they are equivalent. Given one, you have the other. And now, the last missing piece of information right here is the conditional distribution. Well, just like this, the discrete case, if I want to compute the, let's say, how do you say it, the density function with respect to x given y, right? Then what do you think I'm going to do? Well, the definition right there should be what? The density, the chosen density right here for x and y divided by the marginal of the condition right here, y, right? And likewise, if I want to compute f of y given x, what does that mean? I'm going to have the chosen density right here, fxy, divided by the marginal of the condition, which is x. Does that make sense? Right? And likewise, you can also compute the conditional CDF as well. But I claim that is clear because if you know the conditional density right here, you just integrate, you get the other. Right? To get the CDF, you just integrate the density. To get the density, you just take the derivative of the CDF. So no one, you know the other. That's all. Right? And so, for example, and the book doesn't talk about the last case, but I might as well throw that in. That one is so easy. So, for example, the last line right there, what does that mean? You want to compute the CDF, the cumulative distribution of the variable x given the variable y, right? Where x is a, right? And then y right there is just, you know, some y right there, right? Now, what does that mean, strictly speaking? This f right here, that means the cumulative distribution, right? So, that's going to be just like the probability of all the x less than or equal to a. Given that the other variable is held fixed equal to y. Can you see that? Yes?
Isn't it different from minus infinity
To infinity to a. Yes, sorry. This one should be a. Thank you. Yeah, because x right here only go to a. That's it. Right? Does that make sense? Right? F of x given y, and capital F of x given y. Right? One way is you can just think of it like the definition right here. Right? This is nothing but the probability of x less than or equal to a, given that the variable y is held constant, equal to y. Right? So that is nothing but the integral from negative infinity to a of the, how do you say it? The marginal, the f of x given y right here. Or, as I told you already, if you want to compute capital F of x given y right here, what do? You integrate little f of x given y. That's exactly that. Either way you think of it, it's there. Right? Good. So now with everything out of the way, let's do a lot of problems now, because I feel I can feel that you guys are a bit shaky on this type of problem. And I actually realize that most of the difficulties that you guys have are about calculus, how to interpret things. Okay? And then how to determine the limits and things like that, right? And I want you to compute the, what do you call that? The conditional density function of x given y. Alright? So how do I do this? Well, by definition, it's going to be what? Density function of xy, the chosen density, over the marginal density of the condition. It's this guy right here. Right? So therefore, the top right here, just rewrite it like that, and the bottom right here, how do I compute f of y? Just look over your notes. I just tried it right here with you a minute ago, right? To compute the marginal density function f of y, what do? You integrate the Jones density, but with respect to the other variable. Okay, so right here, integrate from negative infinity to infinity of the Jones density over x prime. Is that clear? And now it's all calculus problem. My function f(x,y) right here is defined to be in this box right here, so this one is theirs. Right? And then this integral right here, again, because you do x right here, x only leaves from 0 to 1. So therefore the integral right there is only from 0 to 1 of that. You just integrate that and then do the quotient. Do it. Whatever you get, you get. Is that clear? Good. Look at the next problem. This one is maybe a little bit trickier. So let's not look at the bottom right here. Okay. I want you to, given the function f(x,y), the Jones density function, to be that one. In the first quadrant right here, x positive, y positive, otherwise it's going to be 0. I want you to find what? The probability of x bigger than 1, given the condition that y is equal to 1. Some number right here. So let's see, what are our train of thoughts right here? What should we do? Just brainstorm right here. How do we do that? If we want to compute the probability of x bigger than 1, given y equal to y, what do you? Several ways to do this. Give them a few for me. Name one for me. Probability of x bigger than 1 and capital Y equal to y. What is that? That is the CDF. Correct? Because you want to compute the probability of x bigger than 1. Right? That's the CDF. You have to integrate from 1 to infinity. With respect to x, for example. Right? So now, after I told you that, can you show me how to do this problem? How about if I know how to compute the density function? Little f of x given y. Correct? And then I will just integrate that density function from 1 on. Does that make sense? Right? Right here. I want to compute this thing right here. What am I computing right here? F of xy over fyy. What does that give me?
Density of x given by.
Exactly. This thing right here is exactly f of x given y. Is that clear? And then I'm just going to integrate this guy right here from 1 to infinity. Yeah? Does that make sense? Think about it for a minute. I know that this one is a little bit tricky, so let's take time to absorb it. I want to compute the probability of x bigger than 1, given the condition that y is being held constant, y equal to 1. Right? So, right? Is that clear? In the past, let me backtrack a little bit right here. In the past, if you have just a function of one variable, you know, x, the density function is little f of x, right? What does the capital P of x bigger than 1, what does that mean? That means you want to compute the probability, right, of the variable x is bigger than 1. That means you have to integrate the density function f of x from 1 to infinity. That's what it means in the past. Why do you look at me like that, guys? Now, here. In the past, if you have just one random variable x, right? And if you want to compute probability of x bigger than, let's say, 8, how do you do that? Or even before that, what is the probability of x between A and B? What does that mean? You integrate from A and B of f of x dx, correct? And if you want to calculate the probability of x bigger than A right here, what does that mean? This thing right here means that you compute the probability of x bigger than A than from A to infinity. Right? So you integrate from A to infinity of fx dx. Does that make sense? That's what it is in the past for a function of one variable. Right? And now, in this case, you have two variables right here, f of x, y. And over here, you want to compute the probability of x bigger than 1. Given the condition that y being held constant equal to little y. Right? So therefore, what do I do now? If somehow I can compute the little f of x given the y condition right there, right? Then I just have to integrate that one from 1 on. I will find the probability there. Yep. Okay. So that's the way to do it. Now let's do it. Okay. So to compute f of x given y right here, I'm going to do f of xy by the formula divided by f of yy. Right? So this one right here is this. You put it in, and now you have to integrate this thing right here, because f of y, the marginal density with respect to y, you have to integrate with respect to x of the function. Right? So you integrate x right here from 0 to infinity of that function. Well, because y is independent, I move it out right here, and then I integrate this thing right here. I just see that it's going to give me that. Right? Okay? Don't get lost in the calculation right here. Everybody can do it. Oh, I hope. Right? It's just you integrate it. Right? So don't get lost in this calculation right here. Right? Given time and you are careful, then you will be able to do this. This is a calculus problem. The idea is what I want to get to you right here, to tell you right here. First, I need to calculate the little f, the density, the conditional marginal density right here. And then I just have to integrate it from 1 to infinity. I will get the probability of x bigger than 1. Is everybody clear? Yep. Okay, so that's done. Good. How about this thing? Okay. This one is the example A in the book that I take right here. So now I have the density function, the joint density function fxy equal to that lambda square e to the minus lambda y, where x is between 0 and 1. I want you to first find the marginal density with respect to x and with respect to y, and then also find the conditional density. Okay? So first, the marginal density with respect to x. How do I do it? It's take the integral from negative infinity to infinity with respect to y of the density, of the joint density. You have that. Well, just integrate that out. You have that. Right? It's a calculus problem. Now, how about finding the marginal density function with respect to y? Well, we know that I just have to integrate the joint density function with respect to the other variable, namely y. Namely what? X. Because right here I can find y, so I'm going to integrate with respect to x. There you go. Plug it in. You have that. Right? And now, how about finding the conditional density? What does that mean? I need to find the little f of x given y, and also little f of y given x. Right? So let's do it right here. F of x given y, by definition, is fxy divided by fy. Fxy, well, it's given to me right there. How about fy? Well, we just found out about that in the previous part. From the ratio, you have that. Okay? And likewise, for f of y given x, this is the ratio right there. You have it that way. Is everything clear? Very good. How about this one?
Hey, sir, could you maybe post that online or something?
Sure.
'Cause we just cannot write that fast.
Sure, sure. I will post those online.
Thank you.
You're welcome. Okay. So this right here, I'm just going to do problems with you. All right. And now here's the thing. I'm going to skip a lot from chapter 3 right here, because judging on the questions that you guys have been shooting at me, I'm really worried that if I do that one, I'm going to lose at least half of you guys. All right? Because you know, like you have to do like polar, coordinate, and things like that, transformation, a lot of calculus stuff, implicit function theorem. So I decided to skip that. Right? So over here, and also I'm going to skip the whatever you call it, binomial, bivariate normal, whatever you call it, distribution, right? Because all of those right here, you know, like they're just special case of those right here, where you take the density function fxy to be some binomial distribution. All right? So I'd rather that you have the general idea right there, and later on, if you want to go to a concrete case where f is given by this function, then you can, you know, like apply that one and apply all the properties out. All right. So basically, more or less, whatever I wrote right here, I reviewed for you. That's what you need to know from this chapter. All right. Now, the John density function right here is given like that. In the first part again, I want you to compute the probability of x bigger than 1 and y less than 1. What does that mean? Just think about it right here. How do I compute the probability of x bigger than 1 and y is less than 1? Think about, you know, like the one-dimensional case when you have only one variable. When I want to compute the probability of x between a and b, what do I do? We integrate the density function between a and b, right? And if I want to calculate the probability of x bigger than, let's say, 1,000,000, what do? I integrate the density function from 1,000,000 to infinity, and so on and so forth, right? If I want to calculate the probability of x less than 10, what do? Integrate from negative infinity to 10, so on and so forth. Over here, I want to compute the probability of x bigger than 1 and y less than 1. What do?
Would you do the double integral?
Double integral, exactly. And for x, where does the limit of how do you obtain the limit? Generally speaking, it should be from this one right here, from 1 to infinity, correct? How? Yes, from 1 to infinity. And then what are the limits for y?
0 to 1.
0 to 1, right? Well, strictly speaking, for y it should be from negative infinity to 1, but because the function right there is only defined on the positive, so therefore I might as well cut it from 0 to 1. Is that clear? So, hence the answer. Integrate right here with respect to y, the limit is from 0 to 1. With respect to x, the limit is from 1 to infinity. So you have that. Clear? Now, how do I compute the probability of x less than y?
Like yesterday when you were drawing.
Yes, absolutely. It's always integrate over some region, and you just have to draw it out and see what the region is. So now, how do I find this region? I'm going to do it over here so that you guys can see it. This is my x. This is my y. And remember, x and y are both positive. That means that in general, the function f is defined on the first quadrant only, right? And now you want to compute, you want to look at the region when x is less than y. First of all, what is x equal to y? That's a line going through the origin, right? That's x equal to y. Now, x is less than y. Am I looking at the top half or the bottom half? x less than y is on the top, right? Correct? Because right here, this point right here is the point x equal to y. If you step back a little bit to the left over here, then that means you have y bigger than x, right? So this one is exactly what the region that I'm looking at, right? The top right here. So now, let's say that if I want to do with respect to the x dy right here, I'm going to set up two ways so that you are familiar with it, okay? I realize that this is the part that most of you got confused and got scared right here. So now, what is this? If I do this one right here with respect to y outermost right here, that means that I'm going to, in a way, look at the change in y, correct? And the change in y means the horizontal lines, correct? Because that's the change in y. Go up, alright? So therefore now, y goes from where to where? 0 over here to infinity, right? And now for x, well, for x, the limit for x from the beginning to the end, the lower limit is this one. The upper limit is, how do you say it? This thing right here, correct? The line. So therefore x right here goes from 0 and it bounds by the line right here, and the line is y. So therefore if you do this one, the limit will be from 0 to infinity on the outside and 0 to y on the inside, correct? That's what I choose to do right here, alright? However, you can also do it the other way around, namely the y dx, right? If you want to do dy dx, what are the limits? Okay, so now I'm going to slice x. So that means that I'm going to use vertical lines, right? So let me see if I can find some other color. Okay, so this one right here. Right? So for x, which is the outer limit, x goes from 0 to infinity. Can you see that? And for y, from y right here, the lower limit is going to be this curve, this line right here, and the upper limit is infinity. So it's going to be x to infinity. So if you want to, you can also do 0 to infinity right here, and then x to infinity. If you do dy dx. Is that clear? Alright? So anyway, in the problem, I choose the first one right there, so I get this number. Now, how about if I want to compute the third question right here? Probability of x less than 8. What does that mean? That means that y right there is from negative infinity to infinity. Right? And x right there is from whatever, in the negative infinity to only 8. Right? But over here, because x defined on the positive part, so I might as well cut it from 0 to 8. Is that clear? So therefore I will have just 0 to 8 and then 0 to infinity. Right? Before I say for y, it goes from negative infinity to infinity, but because y is only defined on the positive half, I might as well cut it from 0 to infinity. Alright? So you have that. Alright? And now, I understand that you guys have some questions for homework. Which one do you want me to do? Which one do you want me to look at?
Dr. Nguyen?
Yes?
If possible, are we talking about the homework that's coming up, right? We're not talking
Sure.
about the homework that we
You
just
can
did.
ask me whatever you want. The past homework.
So I'm kind of looking at number 18 and 19. I think I understand number 18 because that was similar to one of the other problems that we did. But if you could get us set up on the functions on number 19, because it's an exponential function,
Okay,
and I'm not sure how the alpha and the beta relate to the lambda. Thank you.
Oh, there is no lambda. Alpha and beta, the row of whatever you call it, lambda. Right here. In the past, whenever you have exponential distribution, what does that mean? f of, let's say, x right here is equal to lambda e to the minus lambda x when x is bigger than or equal to 0, and then it's going to be 0 otherwise, right? That's the, how do you say it, exponential distribution with parameter lambda. Alright? So, by the way, for that, if I say f is an exponential distribution with parameter r, what does that mean? It means that y right here, f of x right here is going to be r times e to the minus rx, where x is bigger than or equal to 0. Alright? When they say parameter right there, that's what I mean. If it is lambda, then it's with parameter lambda. And if they say with parameter r, that means lambda is replaced by r. That's all it is. Alright? And now, suppose that two components have independent, that's the key word, exponentially distributed like times t1 and t2 with parameters alpha and beta respectively. So what does that mean? Let's say that my t1 right here is a function of some time t right here, and this one is with parameter alpha. So what does that mean? Alpha? Yes. E to the minus alpha t, where t is bigger than or equal to 0. Is that clear? Yeah? That's for t1. And now, t2 is also, how do you say it? Exponentially distributed, but with parameter beta, right? And now for t2 right here, remember that t1 and t2 right there, they're function of two different things. So maybe it's best if I write this one as t1 and this one is t2 times t2. Alright? And this one is going to be what? Beta e to the minus beta t2, where t2 is bigger than or equal to 0. Right? Is that clear? It's just like this. If you have f of x right here, it's a function of x, and then you have another function g right here of y is that, and now the idea is you want to form a joint distribution, right? So then you are going to have f of x and y, right? Yeah, but that's are we clear? That's why that's the reason why I want to use t1 and t2 right here differently, because in a minute we are going to consider the joint density function. Alright, so it should be the same thing. Right? So I say t1 is a function of t1, and then capital T2 is a function of t2 right there. And now, remember that they are independent. That's the key word. And remember that half an hour ago when we discussed things right there, we say that the two variables are independent. If and only if what? Their joint density function factors, right? In other words, little f of xy factor into little f of x times little f of y. Or equivalently, their CDF also factors, right? In other words, capital F of xy also factor into capital F of x times capital F of y. Doesn't matter which one you use, all right? So over here, because they are, how do you say it, independent. That means that the joint density now is going to be the what? The product of the two densities, right? So therefore, the joint density is, now I'm going to call it, let's say T, right? T of, well, let's say T1, T2 right here is equal to what? T of T1 of T1 times T2 of T2, correct? So far so good? Right? Okay. Remember that this is only the density function. Okay? So I know that this is a little bit, dangerous right here, because in the past we always reserve the lower letter case for density and upper letter case for the CDF. Right? over here, the Jones density right here, because this is T1 and T1, I'm running out of ways to write that. This is the density they call it right there, so I have to use that, right? So even though this one is capital right there, that's not really the CDF. I just want to give you a head up. Is everybody clear of my point there? Right? If you want to compute the CDF, you integrate this density right. So now the Jones density is that. So now I want to find the probability of T1 bigger than T2. Aha! This is exactly the problem that you just did a minute ago. Right? Except that over here they give you the function T1, T2 this way right here. Right? So now, by definition, what is the probability of T1 bigger than T2? You have to integrate the density function over the regions where T1 is bigger than T2. Right? Okay? So, right here, I'm going to say that this one is equal to the double integral where we find the limits for the regions when T1 bigger than T2 in a minute. Right? But now I know that all I have to do is integrate the density function here. Right? By the way, what is that density function? The product of those two guys. Right? So what is that? It's going to be alpha times beta times e to the, let's say, minus alpha T1 right here, minus beta T2. Right? Because e to the a times e to the b is just e to the a plus b. Right? And now this thing right here is, let's say, what do you want to do? T1 first or T2 later? I don't care. dt1, dt2, for example. Right? Yeah? Or I can also do dt2, dt1. I just have to find the limit accordingly. So now, next comes the question of determining the regions where T1 is bigger than T2. Let's graph it out. It's exactly the same graph right here if you think about it. Okay? So, can I use the same thing right here? Let's say that this guy right here is my T1, X is my T1, and my Y right here is my T2. Right? And if I want to use dx dy, that means that I use dt1, dt2 right here, correct? Yeah? You
Hey, somebody's mic's on.
Oh, sorry.
Mike, I think your mic is on, because we're seeing you.
What?
Someone else is going to
Mike Newsom?
Is
Yeah,
everything-
Mike and Ephraim, hello, we can see you here in Salt Lake. I think your mic is on.
Okay. So is everything okay now?
I don't see a mic on anywhere.
Yeah, sure.
Can you back up a little bit on that T1, T2?
All right, sure.
To go over the integrals again, just, I know it's again.
Okay. So, if you want to compute the probability of T1 bigger than T2, that means that you want to integrate the Jones density function right here over the region where T1 is bigger than T2, right? So that thing is this, the Jones density is just the product of them because they are independent, so I multiply them, I have this, and now I just have to integrate this one over the regions where T1 is bigger than T2, right? So we just have to find out the limit. Suppose that I want to do dt1, dt2 this way right here. So again, it's exactly like the picture that we did a minute ago. Right here, T1 and T2, they are both positive. Right? And now this is the line when T1 is equal to T2. Let's say that with our logic generality, T1 is here and T2 is here. Okay? And now you want to look at the regions where T1 is bigger than T2. That is the bottom now. Alright? So it's down here that we are looking at. And now, suppose that I want to do dt1, dt2. Okay, this way. Then I will, the outer limit right here is T2. That means that I want to use the, horizontal lines, because that's the change in T2. So the horizontal lines are those right here. Okay, so the limits for T2 will be from where to where? From 0 to infinity. Can you see that? This is T2, 0 to infinity. And T1, what are the limits for T1? T1, the upper limit is also infinity because it's go there, but the lower limit is this thing right here, which is the line T1 equal to T2. So therefore this one is T2. Can you see that?
Hold on a second. The limits for T2, 0 to
Infinity,
but
T2.
that's going up.
I'm sorry?
The limits for T2 should be.
Okay, never mind.
I'm sorry?
I think the limits for T2 should be.
Why would it be
T1.
0 to T1?
0 to, because this thing right here, the limit, I'm looking at the T2, right? The slice right here, I will change into T2, right? So I use this thing right here, the, how do you say it, horizontal lines, right? So right here, if you want to use T2, what do you go, what are the limit for T2? It's going to go from 0, to the lines right here, which is just T1. I'm sorry. Yes, only T1, right? Okay, so therefore, this one is not, this is not a good way to integrate, right? Because out here, my T2, if I put this one, it's going to be 0 to T1, right? So therefore, this is not a good way to go. So I'm going to find the what? dt2, dt1, for example.
And I think T1 should be from 0 to infinity.
Let's see. Right here now, dt2, dt1. dt2, dt1, that means that I want to change the, look at the change in T1. That one is the vertical lines, right? So for T1, the limit goes from where to where? T1 is going to go from 0 to infinity. Aha, this one is okay. And then T2, it goes from where to where? T2 will go from 0 to
0 to T1.
T1. Oh, okay, this one is perfect. I don't care about that. So therefore, if I do dt2 first, dt1 later, then for T2, this one is from 0 to T1, and this one is from 0 to infinity. There you go. Right? You just have to draw a picture and then look at, like, it's where the bounds are, and that's all. And now, for B, what is the probability of T1 bigger than 2T2? Oh, it's the same thing. The same idea, because now, well, look at the, how do you say it, the line where T1 is equal to 2T2. What is that? Straight line slope 2. So it's this thing right here. Right? And now, therefore the regions right here, the function is still alpha beta e to the minus alpha T1 minus beta T2. And I learned my lesson already. It looks like better do T2 plus as well, right? So therefore I'm going to do dt2, dt1. And now, that means that I want to, how do you say it, use the, what do you call that thing? Vertical lines, right? And the vertical lines right here, the limits for T1 will be what? From 0 to infinity, and the limit for T2 is from 0 to whatever, the line right here is what? T1 equal to 2T2, so therefore T2 is T1 over half. So this one is T1 over 2. That's all. Right? Because the line right here is T1 equal to 2T2. That is the same thing as saying T2 is T1 over 2. So therefore, this one is exactly the same, except that the limit is going to be from 0 to T1 over 2. That's all. Alright, are we comfortable with those kind of questions now? Yep. What are the things that you want me to do? Even with the past problems.
Dr. Nguyen?
Sure.
Are we going to be expected to do problems number 1 and 2 from chapter 4 on this homework set?
This.
Or are we gonna push it to tomorrow? I'm not sure where we're going here.
So are you comfortable with chapter 3?
Yes.
Can you do all those problems right now from chapter 3?
Mhm.
Yeah? Okay, so, and that homework set is due when?
It was due yesterday.
Okay, let me, if I can just get it out here, that's not it. There we go. So I guess this one is going to be homework number 8, right? So 18, 19, 24, and chapter 4, I haven't touched that one yet, 1, 2. So now I'm going to give you 2 options. Either we wait until tomorrow, and then we can say that the homework will be due tomorrow night, the whole thing. Or we can just do homework 8, just the problems from chapter 3, namely 18, 19, and 27 tonight, and then save 1 and 2 from chapter 4 for tomorrow or next time. Which one do you want to do? It doesn't matter to me.
All tomorrow.
Take a vote. How about we wait until tomorrow and then do everything tomorrow night?
That sounds better to Salt Lake.
Okay.
Sounds great.
Okay. So you know, like you should be able to do the first, the 18, 19, and 27 tonight already, and then tomorrow just 2 problems, very straightforward, and you will be able to do that too.
Dr. Nguyen,
Sure. Go ahead.
this is Debbie from Salt Lake. I'm just pushing a reminder, would you mind making sure these notes get up, because I could not keep up to you, and they were very good examples.
Okay, sure. I will do it. Yes. If not tonight, then by tomorrow morning. Okay? I will post that one online.
Thank you.
You're welcome. And now let me see. I prepare a few other problems as well for you guys to do, just in case, because I don't want to start the chapter 4 right now. What are they? Okay. Let's look at this problem again. All right. The marginal one. This thing. Can you compute for me the let's say probability of let's say y equal to 0 given that x is 0. Do that out all out right here, and then probability of let's say y equal to 1 given x equal to 0, and then probability of y be equal to 2 given that x equal to 0. Okay? Do this one for me. What is this? Probability of y equal to 0, x equal to 0. That's 1. Probability of y equal to 0 and x equal to 0, right? Divided by the marginal probability when x is 0. Yep. Now let's do step by step. What is the probability, the marginal, whatever you call it, marginal x right here? And how did you get it? do you do it? Explain it to me in words. Probability of x equal to 0, that means that I'm going to hold what? And sum across, right? So what is that? X equal to 0, and then you sum for y, exactly that one is 1/2. Is that clear? And now what is the probability of y equal to 0, x equal to 0? Whatever it is, you simplify it. I think it's a quarter, right? And now what is this thing? Probability of y equal to 1, x equal to 0. You see that the bottom is going to be exactly the same, right? And now this one is probability of y equal to 1 and then x equal to 0. What is that? Y equal to 1. No, y equal to 1. X equal to 0. So this is 2/8. Whatever it is. Okay? Now this thing right here is also the same thing. And this is probability of y equal to 2 and x equal to 0. So look at x equal to 0, y equal to 2, 1/8. Over, oh, what is it? This one is 1/2, not 1/3. This is 1/2. Whatever it is. Right? And now, how about probability of y equal to 2 given that x equal to 1? Now you look at P of y equal to 2 and x equal to 1. So y equal to 2, x equal to 1, that's 2/8. Right? So that's 2/8. And what is this? This one means what? The marginal probability when x equal to 1. Right? So what is that? If you hold x equal to 1, where is x equal to 1? Right here. And then you sum over y. So what is that? 1/2? Whatever you have right there. Okay? So on and so forth. We already did all of those. I'm running out of problems that is there anything interesting in the past homework problem? Oh, there is one right here that we can just look at it. Example E, except that I'm not going to give you that, I'm going to derive it for you as well. Example E on page 80. I'm going to ask you this question. Okay, I'm going to let's say that f of x and y right here.
Will you move your paper down, please?
Oh, sure, sorry. Is equal to let's say equal to c. Okay, if this one is page 80, but I'm changing it a little bit. They give you c is 1/pi. I actually want to tell you where that one comes from. Okay? So if let's say, and also I don't want to take the unit this, another word, this of radius 1, I'm going to derive it for general. This of radius r, okay, where r is whatever it is. So if x squared plus y squared right here is between 0 and r squared for some radius r, and then 0 otherwise. Okay. Now I want you to compute c so that f is a density function. Is that clear? Okay. So find c so that f is a density function. Okay. Now, how do I do that? Integrate the function over the regions, whatever the region is, namely in this case it's going to be just, I mean like in R2, right, the whole R2, the whole plan. But you know that outside the, how do you say it, this of radius R, it's going to be 0. So in that case, I might as well restrict my integral into inside the this of radius R. Is everybody clear on that? Right? Because in general, to be a density function, you know that one you write here, you integrate from negative infinity to infinity, negative infinity to infinity, of whatever f of x, y right here, the x dy, and then it's going to give you 1. From there you will be able to calculate c. Right? So therefore I'm going to switch over to polar coordinate, and then it will be okay. So here, this is 1 equal to what? Now how about when I switch over polar coordinates, you know that my x is going to be r cosine theta, and then remember, use polar coordinates. I'm going to review with you over here polar coordinates. It means that my x right here is going to be given by what? R cosine theta, and then my y is going to be given by r sine theta, right? And then my dx dy is going to get changed by the Jacobian of the matrix, right? So in this case, it's going to be r d theta, right? Okay. All right. So here and over here, can you see that the r right there, because I switch over to polar coordinates, so my x and y right now, the function is going to get changed into r and theta, correct? And r right there goes from where to where?
0.
R is from 0 to, okay, here it is bad because it's a, how to say it, this r right here and r right there, so how I write this one as capital R. Is that okay? And then this one is capital R, and little r is for polar coordinates, right? I don't want to, you know, like, so this one is capital R, this one is little r, so therefore my, how do you say it, limit for capital R, for little r goes from where to where? From 0 to capital R, correct? And then my theta is from where to where? 0 to 2 pi. Can you see that? Right? So therefore, what do I have here? F of xy is going to be c. So if I change it over to r theta, it's still c, right? Because it's constant. So this is c. And then the x dy get changed to r d theta. So that means that outside limit right here is from 0 to 2 pi. And this one is from 0 to capital R. So far so good. And now I integrate this. What do I have? I have 1 equal to c. And then let's say that in r right here, when I integrate it first, what do I have? This is 0 to 2 pi, and then this is r squared over 2, correct? And then evaluate from 0 to capital R of d theta, so which is the same thing as what? C right here, and then integral from 0 to 2 pi, still there. And then this one right here is just simply capital R squared over 2, and then d theta. And when you integrate this thing right here, you just pick up 2 pi, right? So therefore you have 1 equal to c, and then this one is r squared over 2 multiplied by 2 pi. And then 2 and 2 cancel. That gives you that 1 is equal to c pi r squared. Therefore your c is what? 1 over pi r squared. Right? So it means that in order for it to be a density function, c got to be pi 1 over pi r squared. Right? Okay? So in the book right here, when you take your capital R to be 1, that is when you take the unit this, then you have 1 over pi. This is exactly this, 1 over pi right here. Okay? That's the density function right there. And now, oh, by the way, physically, you see that this one makes sense. Right? Can you see that this one is just the average over the area? Right? What is the area of this circle? Pi r squared. Correct? And density data is just like uniformly distributed. You just average out 1 over the total area. That's what it means. Okay? So now, if I want to compute capital F of x, little f of capital X of x, what does that mean? I want to compute the marginal density function with respect to x. Correct? Then what do I do?
Fix x, sum over y.
So therefore, yeah, that means fix x and you sum over y. So what does that mean? You integrate the density function over y. Exactly that. You see how things connect to each other. If you know exactly what they mean, you see that way. This is nothing but integral from negative infinity to infinity of the joint density function right here over y. Is that clear? Now, how do I do that? I already know my f of xy is what? There is c, which is 1 over pi r squared. Correct? So now what do I do? This one is integral from negative infinity to infinity. Oh, I may ask, well, how do you say it? Now, I know that outside the, how do you say it, the unit, this is going to be 0. Correct? So therefore, in a way, if I integrate y right here, can you see that y, because x squared plus y squared right here is what? Is less than or equal to r squared. Right? So in other words, if you set it equal to r squared right here, then you can see that y right here is going to be what? Y right here, can you see that it's plus or minus square root of r squared minus x squared? Yeah? Right? So that means that the integral from negative infinity to infinity, I might as well do it from negative square root of r squared minus x squared. Right? To the positive, that one. So allow me to just write this one as minus square root of r squared minus x squared, and this one is to the square root of r squared minus x squared right here. And then this one is what? 1 over pi r squared. And this is dy. Just integrate that. Whatever you get. Can you see that? Right? And now, if I want to compute little f of y right here, what does that mean? The marginal density function with respect to y. So what do I do? Integrate the density, the joint density function with respect to x. Correct? And you do exactly the same. But actually, in this case, can you see that because of symmetry, I actually don't have to do anything. If I already calculate f of capital X, I know f of capital Y. Because symmetry, x and y right there. Right? They're the same. Can you see that? So are we confident now with this chapter? Right? To summarize everything. This is the one that you should remember. If I can find the other page. Oh, right. Okay. Discrete random variable. I'm going to post this as well on the web, but you know, like, try to do it yourself as well so that you know that you can see the difference between them all. Okay? Basically, that's all I want you to remember from this chapter. You know, the bivariate normal distribution, things like that. It's just a special case of this one where your density function takes a certain form. That's all. So I'm not going to go through those. Oh, by the way, I have 1 minute to talk about this. This book right here doesn't talk about it, but I give you a head up right here. If you have a joint density function, f of xy, right here, right? I can also define, I can play this game, define another variable, z equal to, let's say, I don't know, x over y, for example. And then I can talk about the probability of z right here less than or equal to something. Right? Exactly like what you do, what you did in the past, right? So when you do that, you do the, how do you say it? Find the CDF first and take the derivative, and you will be able to find the density distribution for z. Right? I just want to tell you that you can play that game. Right? So on and so forth. Just doesn't have to solve that. All right. So I see you tomorrow.